Hi everyone, we're team BOMS-Probs, and our project is about streamlining material discovery using Bayesian optimization for fluid mixtures, specifically for thermal fluids. So thermal fluids are essential in heat transfer operations, especially when we need to operate over a wide temperature range. However, discovering new thermal fluids is incredibly challenging. Why? Well, because the search space is massive. Hundreds of pure materials and countless possible mixtures exist within this search space, and on top of that, physical experiments to evaluate each candidate fluid is expensive and time consuming. So we asked ourselves, can we guide discovery using machine learning, and in particular use Bayesian optimization to find the optimal mixture to do experiments on? We built a surrogate model using Gaussian processes, which predicts heat transfer coefficients based on four thermophysical properties: density, viscosity, thermal conductivity, and heat capacity. To ensure accuracy, we used Bayesian optimization to tune the kernel type and its hyperparameters. So this allowed us to systematically narrow down a list of over 500 candidate fluids, making the process of identifying optimal formulations faster and more informed, and also we're able to prioritize which experiment to do for which thermal fluid. One of the most critical decisions when training a Gaussian process model is choosing the right kernel, as it governs how the model interprets the relationships between data points. We compared several kernels, and the return kernel stood out because it maximized the marginal likelihood during the first iteration, meaning it gave the best probabilistic fit to our data. But we didn't really stop there. The return kernel itself has hyperparameters, like the length scale, which controls how quickly correlations decay within the input space. Instead of manually tuning it or using a grid search, we used a genetic algorithm to automatically evolve towards the best value. This not only improved the surrogate model's accuracy, but it made the Bayesian optimization more efficient at identifying high-performance thermal fluids. Ultimately, our model became more confident and less uncertain in its predictions. Compared to random search, Bayesian optimization proved to be much more efficient in comparison to random search. It was less sensitive to starting conditions and consistently converged to optimal solutions. This means experimentalists can focus on testing only the most promising candidates, saving both time, resources. However, random search is still shown to be surprisingly good at this task, and I was pretty impressed by this. Finally, we benchmarked three acquisition functions: probability of improvement, expected improvement, and upper confidence bound. Expected improvement turned out to be the most effective, as it balances exploration and exploitation to find high-performing fluids faster. All our code, our methodology, etc., are open sourced on GitHub, and so feel free to scan the QR code and to check out the BOMS-Prob's GitHub to see how we're making thermal fluid discovery faster and smarter. From this project, we were able to streamline thermal fluid discovery and find optimal combinations of thermophysical properties such that the heat transfer coefficient was optimized. Thank you.